Hello folks, we're back with more integrals. Today we're going to go into line integrals, what a line integral means, and how we actually calculate them. So before I introduce line integrals, I'd like to go back and review the basics of a normal integral because that's going to be our motivation of line integrals. By the way, the name line integrals is a bit misleading. It doesn't have much to do with lines. It's got something. It's about curves. It's not about lines. It's about curves. So in the good old days, when we talked about the integral a to b of f of x dx, what we imagined was we have the line segment a to b on the x-axis, and we have a function f of x, okay? And when we graph that function, this integral actually calculates the area below the curve defined by this function on the interval a to b. Okay, that's how we saw integrals as. Now we can try another perspective, and this is going to lead us into line integrals. And what we're going to say is, well, what the function actually does is for each point here, x, right? For each point x not here, it actually just defines a real number value, f of x naught. It assigns each point on the line segment AB a real number. Okay, so what I can think of now is I won't think about an area over an interval. What I'll think about this is that the function f is maybe the density function of this line segment between a to b, and at each point x we're given the density of this, say, wire. We have a wire, okay? It's just like a straight wire between from x equals a to x equals b, and at each point I know the density. So the function f of x just gives me the density at the point x, okay? So the density we know the density for each point of the wire. Then we've seen this before. The integral a to b would actually calculate the integral a to b f of x dx would actually just calculate the mass of the wire, right? Okay, you know the the density of each point, and you do this over the interval, okay? And since the line segment it's just a line segment, it's on the x-axis, it's just going to be a to b f of x dx. Now we'd like to generalize this, and this is where we get into the line integrals. What if we don't have a line segment, we don't have a straight line segment like this, but we have a curve, okay? The wire that we're thinking about is not straight, okay? It's a piece of wire like this, and we know the density at each point, okay? Now again, to find the mass of this function, I'd have to integrate this density over this curve. But what does it mean? It's not a straight piece of line. What does it mean to integrate over a curve? Okay, so how would we, for example, find the mass of this? That's going to be our motivation. Okay, so how would we find the total mass if we know the density? So let's move on. Again, I'm going to go back to the good old single variable integrals for a second. So in the straight wire case, so when we have the straight piece of wire from a to b, okay, we set this up. Why did we set this up? Because it said x starts from a and x goes all the way to b. So we're actually kind of parameterizing this line segment. We're saying that your x is between a to b, okay? So this says that x is just between a to b. No big surprises there, right? And this dx is just a length differential of this line segment, right? It's just the infinitesimal length on this, and we're just evaluating the function. So we got to do the same thing for a curve. When we're given this curve, whatever the heck it is, when we're given this curve c, well, a to b describe the line segment, so I don't know how to describe the curve c yet, so I'm supposed to integrate over this curve c. We'll see how to do it. Of the function f, that might be any good old function that assigns a real value. It might be the density function delta, okay? It might be anything. Now, instead of the length differential here, we need to have the arc length differential, right? Because we need to calculate the piece of infinitesimal piece here. That was basically ds, okay? So on this ds, we're familiar with the term ds from arc lengths. If you're not if you're not remembering what's going on with arc lengths, I would suggest you go back and review that very, very quickly. Hopefully one day I'll have a video up about arc lengths too once I get the Calc 1 instead of Calc 2 and Calc 3. But I would highly suggest you review your arc lengths. So our length differential here, infinitesimal length, is called ds, and we know a lot about ds, right? For example, if we're talking about a curve described in terms of a parameter t, so we're going to usually, when we talk about curves, they're described in terms of a single parameter. We think about time. At which time are we at time t, where are we, at which point are we going to be at time t? So both the x-coordinate and the y-coordinate are described in terms of t, and t is on some interval, say t starts from 0 to 1, or some time interval, okay? Then this curve would be, integrating over the curve with respect to ds would be a to b, and instead of f of x, y, I would plug in x of t, y of t, which I get from the curve, and then ds, this piece here, dx dt squared plus dy dt squared in the square root dt. Remember, this was ds. This was what we saw from arc lengths, okay? The proof is not that bad. You're trying to approximate the arc lengths using line segments. It's going to be in every calculus book. Again, hopefully one day I'll put a video up showing that also. For a function of 3 variables, it would be the same thing. Integrating over the curve, this line integral, again, I'm sorry, it's going to be a curve, f of x, y, z ds, is the same thing as we plug in the x and y and z from the curve. We pull that out from the curve, and then it would be dx dt squared, dy dt squared, dz dt squared, all in the squared dt. Now, this term, actually, there's an easier way to remember this. It doesn't make calculating the integrals any easier, but there's an easier way to remember this. Remember, given if c is the curve described by r of t equals g of ti, h of tj, this is in 2 variables. You can have it in 3 variables if you want. You know, there could be a k term also. Then dr dt, remember we did this, dr dt is just going to be what we call v of t, okay? So this term is actually the length of v of t, which is kind of like the speed. So if you to make it easier, if you know how to calculate v of t and then its length, this is just the curve, the line integral over the curve of the function f ds, is just plug in the variables, and you're just plugging in the speed dt. Okay, length of the velocity, the magnitude, sorry, of the velocity is speed. So this is your formula. This is in 2 variables. You could have it in 3 variables. You could have it in 4 variables. You name it. This is how you calculate it. Now, this we're going to see later. Sometimes there's like a circle here on the integral. That means the curve is closed. Okay, so that means you have a curve that is closed. It ends up where it started. For now, I'm not going to do any closed examples. We're going to do them later on. If you see a circle, so don't get scared. It just means the curve is closed. It's a closed curve. That's important in physics and whatnot. All right, so we've gotten this. This formula is very important. So whatever the function, how many variables, I didn't write any variables here because that depends on the problem, of the curve, okay, ds, with this line integral is from a to b. You have a parameterization of the curve, r of t, and you're trying to get the speed dt, f times speed dt. And that's going to be your integral. Okay, so I think it's high time we do some examples. So I picked some pretty easy examples that we can go over. And the first one is, let C be the piece of the circle x squared plus y squared equals 4. So it's the circle centered at the origin of radius 2, but we're only limiting in the first quadrant. Okay. So in that case, I would like to evaluate this function x squared y over this circle ds. So maybe the density at any given point here, xy, the density at the point xy is x squared y, okay? So what would be the mass of this wire, this piece of wire, if it's got different densities at each point and the density is given by this function? So let's remember how we parameterize the standard parameterization of the circle. Remember, the standard parameterization of a circle was x equals r cosine t, y equals r sine t, where r is actually the radius of the circle. Here, the radius of the circle is 2, square root of 4. So we're going to use the parameterization x is equal to 2 cosine t, y is equal to 2 sine t. Okay? Now, these are pretty easy functions. Let's calculate ds. Remember, ds was speed dt, or in other words, square root of dx dt squared plus dy dt squared. Okay, so dx dt would be just minus 2 sine t, square it, and dy dt would be just 2 cosine t, square it. And so this is going to be, I pulled the 4 out, there's 4 in both of them. It's going to be, minus signs are going to be gone. Sine squared plus cosine squared t, that's going to be 1, of course, so you just have the square root of 4 dt. That's going to be 2 dt. So the term, this term ds, is actually for us just 2 dt. Now, what describes, given this parameterization, what describes an object moving along this curve is, well, at point 0, you're over here, and at point pi over 2, t equals pi over 2, you're going to be over here. Okay, that's why it's called the standard parameterization. It's basically the angle, right? Angle 0, angle t pi over 2 in radians. So the integral is going to be from 0 to pi over 2. We're using this parameterization. Now, it's very important. The original function, if you remember, was x squared y. We can't use x squared y anymore. Into x, I'm supposed to plug this in, and into y, I'm supposed to plug this in. So in wherever I see x, this is going to be x squared, and this is going to be x squared, and this is going to be y, right? Because x was 2 cosine t, y was 2 sine t, so x squared is going to be 2 cosine t squared, and y is going to be 2 sine t, and this bit over here was ds, okay? And again, because t was, when we parameterize it, t ranged from 0 to pi over 2, we do the integral from 0 to pi over 2, okay? So now what we're going to do is we're going to factor this out. We're going to have a 4 from here. We're going to have another 2, that's an 8. Another 2, that's a 16. I pulled the 16 out right over here, okay? Still the integral is from 0 to pi over 2. We have a cosine squared times sine t dt. And this is just a simple substitution problem. If we call u equals to cosine, du is going to be minus sine t, so we need a minus. So all we have is actually minus 16 u squared du. The integral is, of course, going to be minus 16 u cubed over 3. Plug it back in before you evaluate, of course. Minus 16 cosine cubed over 3. I plugged u back. And we want to evaluate it. Oh, that's messed up, right? Sorry, not the integral. The evaluation from 0 to pi over 2. And plug in pi over 2, you get 0. Minus and minus is going to make a plus. Plug in 0, you get 1. So 16 over 3 times 1. Okay? So a very simple one. Now, all the problems that I picked for these sections, the ds term is constant times 2 dt. In the next problems, I think it's going to be 3 dt. But they could have, it doesn't have to be a constant. This could be a function of, ds in general could be a function of dt. Okay, so there could be like d cubed dt here or something like that. We're trying to keep the integral simple here. We're just trying to, again, try to teach you how to do the integral, how to set up the integral, and we're not trying to make the integrals themselves very hard. Solving them is always another method. At this step, of course, you want to learn how to set these integrals. That's more important than actually solving them. Okay, so let's do another example. And for this example, we're going to evaluate the function xy, y squared plus y squared plus z over this curve C. Okay, and what is this curve C? This curve C is parameterized by r of t. Remember, we saw this before. This is the distance from the origin as a vector. So we have 2ti, tj, 2 minus 2tk as a vector. Okay, so it gives the distance vector from the origin. Now, in the problem, we want to go follow this curve between 0 equals, between t between 0 and 1. So, first of all, we just again write our formula down. What was our formula? Evaluating on this curve is the same thing as we evaluate on the curve. He's not C anymore, so 0 to 1. And we're going to plug these in. We need to calculate again the square root of the magnitude of the velocity, the speed dt. So let's find the derivatives here. Dr dt of this vector, I'm differentiating the vector. It's going to be just with respect to t, this is just going to be 2i, and this is going to be j, and this is going to be minus 2k because derivative of 2 is 0. So then if we find the length of this, that's going to be 2 squared plus 1 squared plus minus 2 squared, which is again 2 squared. So square rooted, you get 3. So our term ds is just equal to 3 dt. Remember, this was the speed times dt, so it is just 3 dt. So now we can evaluate this curve, the integral over the curve, xy plus y squared plus z ds. And how can I evaluate that? Well, it's going to be from 0 to 1. Now, remember, I'm pulling the x from the x component, of the vector here. So that's going to be, I'm going to plug in 2t for x. This is going to be x. And I'm pulling the y from here, from the y component. So I'm pulling t for y. Okay. So then, of course, this is going to be y squared. And this is going to be z because this is z component. Okay, so you're pulling these, you're plugging into these because your values have to be on the curve. You're pulling them from the curve itself. Okay, times 3 dt because this was our ds. Okay, so let's get down to the evaluation part of it. This is going to give us 2t squared, 3t squared. There's going to be a minus 2 from here and a plus 2 times 3 dt. I pull the 3 out. Then you're going to have 3t cubed over 3 minus 2 squared over 2 plus 2t. Evaluate from 0 to 1. Of course, these are going to cancel. You're going to get 2 from here. 3 times 2 is going to be 6. Again, as itself, I mean, after we set the integral up, solving the integral up was kind of easy. Guys, I mean, because you have a square term here, usually... the reason we're doing constants and stuff is usually if you have terms with t's in them, clearing this out might be a nightmare. Okay, remember, square terms might be a nightmare. Hopefully, maybe you could do trigonometric substitution or something like that on it. That's why we're keeping these dt's. ds is very simple because in general, clearing out squares is not nice, right? Okay, so now I want to do an integral over a piece of line, actually, okay, over a line segment. So we've been doing these over these curves, whatever these curves look like. First one with the circle, I have no idea what this looks like. Well, we could plot it in, but let's not worry about it. Let's talk about this. Oh, it's a line. Anyways. That was a line also. All right. Anyways, let's talk about a line segment. And we're going to evaluate this function x plus y plus z. Very simple again. We're trying to keep the integral simple. Over the curve, where the curve is the line segment. Now they're giving us from 1, 2, 3 to minus 1, 0, 2. Okay, minus 1, 0, 2. So let's call this point P. Let's call this point Q. And what we're going to see is that we need to remember to get the parametric representation of the line segment, we need to do this guy minus the endpoint minus the beginning. So the vector PQ, minus 1, that's going to be minus 2. 0, minus 2, that's going to be minus 2. So 2 minus 3, that's going to be minus 1. So the vector PQ going from this point P to this point Q, right, is this vector, okay? So now, to get the parametric, we just basically slapped on a t and we added the starting point. So we could do 1 minus 2t, okay? I'm getting the minus 2t from here. 2 minus 2t, I'm getting it from here. And 3 minus a t, I'm getting it from right here because that was minus 1. What would be the vector representation of this curve, of this line? It would be r of t 1 minus 2ti, 2 minus 2tj, plus 3 minus tk. Okay? So again, so linear, this is a line. Now we want to integrate this curve over there. So let's do it. So I rewrote r of t on this space, so it's right in front of our eyes. Again, we calculate dr dt. We get minus 2i minus 2j and minus a k. Derivative is minus 1. So magically, of course, the numbers work out to be magically when you take sum the squares and take the square root. Again, it's 3. It's a lovely number, isn't it? Pythagorean triple right there for you. So when we integrate this function x plus y z, x plus y plus z ds over this curve, what we're actually doing is t, oh, sorry, I didn't show you that. So here guys, t is gonna, when you get the parameterization of the line, t is gonna go from 0 to 1. And the way you check that, just to make sure you got the right parameterization, is when you plug in 0, you should get 1, 2, 3, you should get the original point. And when you plug in 1, you should get this point, right? Minus 1, 0, and 2. So I got that point. If you did it right, okay, basically, again, you calculate the vector, then you add this point to the vector, the original point to the vector, and that's if you do 0, t between 0 and 1, that's always going to be the correct parameterization. So for us then, this guy at this step now is when we're integrating over the curve, we're trying to do t goes from 0 to 1, and again, we're pulling these x's from here, right? This guy is x, this guy is y, this guy is z, and the function was x plus y plus z, so I just wrote them here, x plus y plus z. We have, this is our ds. So that's going to be minus 2, minus 4, minus 5t, plus 3 is 6 dt. So we have the 3 outside, don't forget your 3. And that's going to be minus 5t squared over 2 plus 60 evaluated from 0 to 1. So it's going to be 3 times 6 times minus 5 halves, and that's going to be, so that's going to be 7 halves times 3, that's going to be 21 halves. Okay, so I'd like to conclude this section for our engineer friends and physicist friends, some useful identities that you get from these from these line integrals, from these integrals over these curves. First of all, the delta is a density function. Okay, so you put in, however, if you're in 2 space, it's got two variables. If it's in 3 space, it's got 3 space. So again, we're thinking about the mass of a wire. When you have the density each point, you just do the integral ds over the curve. What about moments? Around about the coordinate axis? Well, you have the first one is going to be c is going to be x times delta ds. We talked about this before, and we're going to do m sub xc is going to be over the curve interval of y delta ds, and m sub xy is going to be on the about the xy plane. That's going to be z times delta ds. Okay, so basically how far you're going out from the plane. That's how it's measuring times the density. Now then, the center of mass is, we're going to divide the moments. So the x coordinate, x bar of the center of mass, the centroid, would be this value over the total mass, and the y coordinate would be this value over the total mass, and the z coordinate would be the moment about the xy plane over the total mass. Again, the total mass itself is just over the curve. You would need to calculate the delta ds. So there's 4 integrals you need to calculate here. You need to calculate, say, these 3 integrals, and then you need to calculate this without the delta ds to calculate the mass. What about moments of inertia about the axis? About the x-axis, it's going to be y squared plus z squared times delta ds. About the y-axis, it's going to be x squared plus z squared delta ds. Again, the appropriate variable is missing. About the y-axis, of course, y is missing. About the x-axis, x is missing. Similarly, about the z-axis, the z component is missing. X squared plus y squared times delta ds. What about the general line? What about a general line, L? Well, that's going to be, this is actually the distance from that axis, right? So this is the distance of the point from the x-axis. So what we're doing actually is r squared delta ds, where r of xyz is the distance from the point xyz to the line L. So that would give you the inertia about the general line. So these would be applications of line integrals for physicists and engineers. Real life applications, you would use these formulas. So again, of course, I'm going to suggest that you open a good old calculus book. Any calculus book is going to work, and do some problems using line integrals. Next time we're going to try to apply our knowledge about line integrals, and we're going to introduce vector fields and see what happens over there. Take care. Bye bye.